like you to now engage in a thought experiment. So here we have two balloons. They're filled with hydrogen gas and oxygen gas. And I'd like to point out that both balloons are at the same pressure, temperature, and volume. So I'm just going to remind you about the ideal gas law here. PV is equal to nRT. So both balloons contain gases that are at the same pressure, temperature, and volume. So pressure's the same, volume's the same, temperature's the same. Perhaps you can get the idea that both balloons also contain the same number of particles, because if three of the variables are exactly the same, well, then the fourth has to be exactly the same. So given that they're at the same temperature, so I'll just write it this way, they're at the same temperature, this would suggest, of course, that both the hydrogen gas and the oxygen gas have the same average kinetic energy. But then I asked the question, the balloons are leaky. And actually, this is true of any balloon. There's no balloon that you could get that you would fill it up with air and then, or some other gas, and that you'd expect the balloon to remain inflated forever. So the balloons will be leaky. And let's assume that they're both leaky, and they're both leaky to the same degree. But then I'm asking, which balloon will deflate the fastest? So let's make this as a little bit of an interactive question. So let's say the hydrogen gas corresponds to balloon A, oxygen gas to balloon B, and then I'll give a third option where, just to play devil's advocate, C is going to equal deflate the same. And I'd like you to make a pick as to which choice you think applies in this case. So now you probably found out that it's the balloon that contains the hydrogen gas that will deflate the fastest. And so here's the issue. Although both gases have exactly the same average kinetic energy, this does not mean that both gases' particles are moving at the same speed or velocity. As it turns out, the speed or the velocity also depends on the mass of the particle. So the energy is the same, but because the masses of these particles are different, the particle that has the lower mass will be moving more quickly. So to help you understand this, I'd like to draw your attention to an equation which essentially outlines this idea. So we acknowledge that the average kinetic energy is proportional to the temperature in Kelvin. Now this equation, however, is found on your formula sheet and is derived from thinking that the average kinetic energy, essentially energy, can be related to the speed of a particle based on our kinetic expression as the following. So we can go energy is equal to 1/2 mv squared. And so you can see that the speed of a particle does depend on the energy, but it also depends on the mass. Now, it's a little bit more complicated because we're dealing with many billions of gas particles. So taking that into account, we arrive at what's called the root mean square speed equation. So essentially, it is derived from this very famous physics equation. But with a little bit of manipulation, we end up with this 3RT over m. Now the 3RT is related to the average kinetic energy. So as you might expect, the greater the average kinetic energy, the greater will be the speed of our particle. And if you want, it might be helpful to think of this is kind of like an average speed. So we call it the root mean square speed, or if you want, root mean square velocity. Again, chemists are not so concerned about distinguishing between speed and velocity. I know velocity has a directional component or a vector component, but in chemistry this is not as important in this particular example, so we use those terms interchangeably. So the 3RT is related to the average kinetic energy, and as you might imagine, this big M has to do with the mass. Now, I'll explain why we use this symbol in a minute, but just to be clear, if this is the mass, well then the greater the mass, being in the denominator, the slower will be the speed. And so hopefully it makes sense to you that oxygen's particles, although having the same average kinetic energy as that of hydrogen, they'll be moving at a slower speed. So let's unpack this equation a little bit more. Again, this equation is found on your formula sheet, and you may be asked to do a calculation with it. But I think what's more important is that you understand the significance of the equation. So as I say, this term here stands for root mean square velocity or speed. It's kind of like an average speed. And in this case, R is the same ideal gas law constant R that we saw before. But if you take a look at your formula sheet, you'll see that there are other possible units for R. So the R that we met originally had the units liters, bar, mole, Kelvin, and it was 0.08314. Well, in this case, we're now using the term, or R, in terms of units of joules per mole Kelvin. In order to understand a little bit better how R is playing a role here, joule, of course, is a term for energy. A joule can be thought of as a kilogram meter squared per second squared. So just to help you out with that a little bit, perhaps people remember that work can be thought of as a force times a distance. Force can be thought of as a mass times an acceleration. And in terms of mass and thinking about the standard unit for mass in physics, we say kilogram. Acceleration is meters per second squared. And of course, our distance here is meters in terms of the units. So collectively, that stands for kilograms, meters squared per second squared. And all of this is therefore equal to a joule. So again, we need to use the R term here that's related to energy. If you use the other R term, you're going to get the answer incorrect. Now, the other thing that we need to mention is, while I just simply indicated this capital M corresponds to mass, it has to be the molar mass of your gas in kilograms. And perhaps you see why, because our R term is also in kilograms. So this is why I just don't put a lowercase m. Now, of course, there's a little bit of a confusion here because we also know that that m could stand for molarity. So hopefully you appreciate in this context, this corresponds to mass in kilograms. In a minute, I'd like to do a calculation with you involving this equation. But before I do that, I'd like to show you a simulation that shows you how speed or velocity of a gas is related to temperature, but also the mass of the gas. So in this simulation, you can see that we have a representation of hydrogen gas particles. They are currently at 100 Kelvin. On the right, you see something similar to a Maxwell-Boltzmann energy distribution, except now it's a velocity or speed distribution. The y-axis is shown as probability, and the x-axis is shown as velocity. So we've just increased the temperature to 200 Kelvin. You can see that there's the most probable velocity, which is indicated by the dashed purple line, and then also the root mean square velocity. So again, the average velocity or the root mean square velocity is skewed a little bit to the right because of the fact that we have particles that have really high velocities, and we don't know exactly what those velocities are. So as you can see, as we increase the temperature, the curve in this graph is flattening out, if you will. Fewer and fewer particles actually have the most probable velocity, but we have more and more particles at even higher velocities. And also you'll notice that the average velocity or the root mean square velocity gets higher and higher with these higher and higher temperatures in Kelvin. In the simulation, you can also see that the gas particles are moving more quickly, but again, not all the particles are moving at the same speed, and that's exactly what this distribution is showing us. That is, the graph distribution is showing us that some particles move very quickly, some very slowly, but there will be this average speed. So I like this simulation because it gives you a sense that, again, not all particles are moving at the exact same speed. They're colliding with one another, and in a sense, they're exchanging energy. And so at one moment, one particle is moving slowly, and the next moment, that same particle is moving more quickly. Now let's move to looking at what happens when we change to helium. See, helium is more massive than hydrogen. And I think you can notice already, and I'm just going to pause the video for a second, that this has an effect on the root mean square velocity. So perhaps it might be worth just for a minute going back to the hydrogen here. So you can take note. So hydrogen at 500 Kelvin has a root mean square velocity of 2,487 meters per second. So look at what happens to that velocity at the same temperature. So of course this means the same average kinetic energy, right? But we're now dealing with a more massive particle. So think 2487, and then now we'll change this to helium. And now the root mean square velocity has gone down to 1766, simply because we have more massive particles. So again, the same average kinetic energy, but a more massive particle. And then now we move to nitrogen, and you can see the root mean square velocity goes as low as 667 meters per second. And indeed, the simulation is showing that the particles are moving more slowly. So in all cases, all three gases had the same average kinetic energy, but of course they'll have different speeds. So now we turn our attention to carbon dioxide, and this is an even more massive gas at roughly 44 grams per mole, and you can see that the velocity is 532. We now went back to water. Water is less massive, so its root mean square velocity in the vapor state is around 832 meters per second. So hopefully this simulation has helped you appreciate that indeed the speed of a particle, one, depends on the average kinetic energy, which depends on the temperature, but two, depends on the mass of the particle. So now let's turn our attention back to the notes and doing a calculation with this equation to see where those numbers for the root mean square speed or velocity came from for those different gases that we were looking at. So this question is found in your course pack. It says here, calculate the root mean square velocity or speed for oxygen at 25 degrees Celsius. Now this problem in terms of doing a calculation is super easy, but there are some spots where it's really easy to make a mistake as well. So here's our equation. Then we need to start to unpack the information. So number one, we need our R value. And to make sure that the units cancel properly, I'm going to use the version of joules as kilograms meters squared per second squared, mole Kelvin. And then we have the molar mass of oxygen. Now note, I need to express it in kilograms. So instead of just 32 grams per mole, it's 32 times 10 to the negative 3 kilograms per mole. And of course, I need to express my temperature in Kelvin. So now let's plug in the values. I hope you see that when we plug in the values in this fashion, well, indeed, the kilograms are going to cancel. Our Kelvin will cancel. Our moles will cancel. And then we're simply left with the units meters squared per second squared. But of course, we're taking the square root. So we'll have the final units of meters per second. So then I do the mathematics, and then I'm going to take the square root, and I end up with 482 meters per second. Now, I'd like you to reflect on this number for a minute. That's half a kilometer in a second. So again, a thought experiment. If you could grab an oxygen molecule in your finger and then release it, within 1 second, it should move a half a kilometer down the street, if you will. The issue is it probably wouldn't make it there. That is, it wouldn't make the full half kilometer in that 1 second because it's going to collide with other oxygen molecules and, of course, nitrogen molecules. It might hit a car. It might hit a lamppost. It's going to collide with other things. But if it had a clear chamber, it would certainly move that half kilometer in 1 second. So in our live sessions, we're going to use these principles to explore the concepts of diffusion and effusion.